So thank you very much for having me. Today, I would like to discuss our latest paper, which is called How to Calibrate a Climate Model with Neural Network-Based Physics. And I've been working on this paper with David Saint-Martin and Aurélien Rib from CNRM, Météo-France in Toulouse, France. So I think that you're all familiar with climate modeling, but I would like to make a small introduction on climate models. So a climate model resolves a set of partial differential equations called primitive equations. And since the set of equations contains Navier-Stokes equation, we don't have any analytical solution yet. So, but we can construct an approximate solution to this set of equations. But for this, the equations need to be discretized on the model's grid. There is a set of grid points that define the domain of a climate model. In our case, the domain is the globe itself, and the horizontal resolution of a climate model is the distance between two neighboring points, which is in current classical or standard climate models about 100 or 150 kilometers. The equations are also discretized to describe the vertical structure of the atmosphere. To each grid point corresponds a column, which where the equations are discretized on several vertical levels. For example, in the case of Arpège Climat, which is the model that I am working with, there are 91 vertical levels from the surface to the top of the atmosphere. But at a resolution of about 100 kilometers, the discretized equations are insufficient to represent some processes called fine-scale processes. Here on this precipitation map, I have represented a box, the size of which is about 150 kilometers and which is centered on Toulouse. And you can see that there are quite a lot of precipitation inside of this box, and the equations are not sufficient to represent that. So to represent these fine-scale processes, we develop physical parameterizations, which are parametric functions. In the case of our climate model, Arpège Climat, which has a resolution of 100 kilometers. These processes are non-orographic and orographic wave drag, cloud radiative transfer, latent and sensible heat fluxes, turbulence, atmospheric chemistry, and what interests us a lot, deep and shallow convection. So current physical parameterizations are developed using observations, theoretical knowledge, and output from high-resolution models. They are built to be numerically very efficient, but this comes at a price of uncertainties, so that current physical parameterizations remain the main source of uncertainties in climate models. This results in biases in climate models or in climate projections, part of which are well known. As an example, parameterization, the use of parameterization results in a poor representation of the diurnal cycles of convection or of the Mendelian oscillation. But since 2018, there is a new kind of method to design parameterizations, which uses artificial intelligence techniques to learn the representation of subgrid processes from high-resolution model outputs. I think that you're all familiar with neural networks, but just a few words on it. As well, so neural networks are nonlinear applications that I will note as hat in the following. I would consider only feed-forward neural networks, so very simple architectures for this study. And they are defined with a set of parameters lambda, and they assign to x the value y. So the application of this method allows the construction of data-driven parameterization, and the literature, which has been growing since 2018, reports very good results. So the first papers were, for example, Bernard and Bertin 2018, Gentin et al. 2018, and Rast, Richard, and Gentin 2018. To illustrate these good results, I'm sorry, the titles are in French, but I will translate them. I took this figure from Rast, Richard, and Gentin 2018, and it represents the mean convective and radiative subheating rates, so subnuclear processes. And there is a high-resolution model, which makes quite accurate prediction for this quantity. And as you can see, the physical parameterization that I have, that you see in the red box, has a bias in it. This is the intertropical convergence zone, which is double, and this is something that we don't have in observations. And when you replace these physical parameterizations by neural network-based parameterizations, you see that the bias is no longer here, and the results are closer to the high resolution or high fidelity model. So these results are encouraging. However, if neural network and artificial intelligence, data-driven parameterizations are not used more extensively, is because there are some issues that need to be addressed. The first of these issues are stability issues. This is something that we have also studied previously, but today I would like to focus on a second issue related, linked to the online performance of neural network-based parameterization. So to sum up what I've said in this introduction, a climate model can be resolved equation 1. So the time derivative of x is equal to the dynamics, which corresponds to the discretization of the primitives equation, plus the parameterizations, which also depend on x. X is a variable that describes the thermodynamic state of the atmosphere. So there is one distinction that I would like to make at the beginning, which is very important to quantify the performance of a climate model and the parameterization. So there are two ways, at least, to evaluate a physical parameterization's performance. The first one is the offline performance. This is a performance that can be measured on an external sample. And offline performance is what we compute traditionally on neural networks after the training on a test data set. So this is one thing. But what really interests us is the online performance, which is the performance of the parameterization once it has been implemented into the climate model. So this can be evaluated by measuring the error on some quantities that interest us. For example, one quantity that can be interesting is the climatology of the model, like mean global temperature in a log simulation. The parameterization that is used will have an impact on it, and the error is computed with respect to observations, for example. So the physical parameterizations are parametric functions that are defined with a small number of parameters The small number, by small number, I hear from 10 to 100 parameters. And they are first optimized offline, so on an external data set. Then part of these parameters, which are identified to be sensitive parameters, are also optimized online during something called tuning for the development of physical parameterization. And tuning is meant to guarantee that a good online performance to these physical parameterizations. But when we take a look at how it's done for neural network-based parameterizations, current neural network-based data-driven parameterizations can only be tuned offline. And so there is no guarantee that they will be accurate once they have been plugged into the climate model. So one question we can ask is how to make these data-driven parameterizations possible to calibrate, and so how to calibrate a dynamical system with neural network-based physics. The answer that we have to this question is a method to develop data-driven parameterizations that can be calibrated, and it can be described through 3 steps. The most important step is step 1 towards getting parameterization that can be calibrated online, and this step 1 consists in generating a new learning sample, which samples X, Y, and also theta, where theta are parameters that we have identified to be sensitive, and which we also sample to build the learning sample. We then train a neural network F hat to approximate Y, which are subgroup processes as a function of X and also as a function of theta. And then the last step consists in implementing this data-driven neural parameterization into the climate model, calibrate the value of theta, notice theta star, the optimal value will be noticed theta star, and this optimal value will be used in further simulation. So in the following, I would like to illustrate this method using 2 examples, which are examples on toy models, on Lorentz toy models, which are the Lorentz 63 and the Lorentz 96 toy models. So for the first example, I will focus on Lorentz 63. The system of Lorentz 63 is defined with a set of 3 differential equations. The state variable is X. There are 3 coordinates, and the system is also defined thanks to 3 parameters, which are sigma, rho, and beta. And equation 4 corresponds to the time derivative of x3. This part of the equation can be viewed as a kind of a parameterization, which depends on a variable beta. So for this first case, the neural network F hat will learn to approximate this equation 4, the parameterization as a function of x1, x2, x3, which is the Lorentz 63 state variable, and also as a function of beta. So then we apply the first step, and the learning sample will be obtained by generating several L63 time series, also called orbits, in which we have generated using several values of beta and x1, x2, x3. And the learning sample will look like this: x1, x2, x3, x, and beta, and x3 dots, so the time derivative of x3. the parameter theta that we will optimize will be here beta, and the optimal value will be computed with respect to a reference data set. In the case of a climate model, the reference data set can be typically observations, reanalyses, or output from high resolution model. In the case of Lorentz 63, we don't have any of that. So the reference data set will be a time series that I will note X0. Integrate that was generated by integrating equation 6, which corresponds to the Lorentz 63 equations that we have parameterized with reference values of sigma, rho, and for the two parameters sigma, rho, and beta. And the orbit is long enough so that the mean value and the standard deviation no longer depend on the spatial initial condition. So once we have this reference data set, the other thing that we need to make the calibration of the value of beta is a metric that we will minimize in order to get the optimal value of beta. So in our case, and what we would like to calibrate in Lorentz 63 is the long-term climate, which corresponds to mean value and the standard deviation computed on long time series generated by integration of equation 7. So this is the same that what we use to generate the reference data set, except that the coordinate x3 dot is replaced by the neural network parameterization. And so a very simple choice of metric, of the minimization metric that I will note M in the following, can be expressed as equation 8. So M beta is equal to the L2 norm of differences of the error between the mean value computed on x f hat, so the orbit generated by integration of equation 7, and the mean value computed on the reference orbit, and the same difference between standard deviations, so computed on orbits generated with the neural network-based parameterization and on the reference dataset. The following slide will give an illustration of the metric M as a function of beta. Here you can see a graph where each red dot corresponds to a time series or orbit of Lorentz 63, generated by integration of the Lorentz 63 equation. So with the third coordinate governed by the Lorentz 63 equations as well. And as you can see, the metric M reaches a minimum at approximately 2.6 or 2.7. This minimum is materialized by the dashed red line. And this is the value of beta in the reference data set, which is a third equals 2.667. So the metric that we have chosen appears quite good to make the minimization of beta. And here I have represented again the value of metric M for several values of beta, and each light blue dot corresponds to an orbit that has been generated by integrating the equation that you see, where the third coordinate, so the parameterization, was replaced with the neural network. And as you can see, the curve is reaches also a minimum, and this minimum is reached at the optimal value of beta, noted beta star, and numerically beta star is 2.664. This is also materialized by the dashed blue line As you can see, the reference value of beta and the optimal value of beta are very close. So logically, we have recovered the value of beta used to generate the reference data set. So far, our method seems to work quite well. But now we can focus on a second example using another Lorentz toy model, which allows us to do some really interesting things. So the second toy model is Lorentz 96, which is also a system of parametric equations. The parameters that will interest us are F and C. And this equation describes the evolution of a large-scale variable, x, that is coupled to two fine-scale variables, y. And schematically, we can write the equation linking x, the equation giving the dynamics of x by equation 9. So the time derivative of x is equal to kind of dynamics of x, so large scale, the evolution of large scale variables, plus a forcing term f, plus a coupling term b, which depend on y, which are the fine scale variables, as well as on c, which is a parameter. So the machine learning task will be to learn b, the coupling term, as a parameterization, f hat, which depends on both x and c. And the resulting dynamical system, once the coupling term has been or parameterization has been replaced by the neural network estimate of this function, is given by equation 10. X dot hat equals the dynamics plus the parameter f, which is the forcing, plus the neural network emulation of the coupling term. So here we will proceed the same way that we did in the Lorentz 63 example. So first we generate a reference data set. Here neither, we don't have observations, so it will be again a long time series obtained by integration of equation 11, which corresponds to the Lorentz 96 equations that has been parameterized with f and c, the two parameters equal to reference values f0 and c0, and numerically f0 and c0 equals 10 and 10. The second thing we need is, as in the first example, the metric m. And here m, we take the same type of metric than before, than in the previous example, but here it depends on c and no longer on beta. And a particularity of Lorentz 96 is that the mean value does not depend on any parameters because it always equals 0. So the first term can be simplified, and the metric corresponds only on the error on standard deviations computed on orbits obtained by integrating the equations with the neural network parameterization and the standard deviation computed on the reference dataset. And now we can apply the method that I have presented in two cases. So the main task will be to find the optimal value of C for the equation x point hat equals the dynamics of x plus f hat, the neural network parameterization depending on x and c. And I will consider two cases. The first case is the ideal case. As you see in the equation in the box, there is a parameter f, and the first case, the easy case, I would say the ideal case is the case when the parameter, the forcing parameter, so f equals f0. Here the errors come only from neural network parameterization. However, in a more realistic case, in a climate model, there are some parameters that cannot be tuned, the value of which cannot be tuned, but which can introduce biases into the simulations. And in order to replicate this more realistic case, the second application of the method, which I called imperfect model calibration, will implement another value of f that is not necessarily equal to f0. So we put a bias on f, and the task here will be to try to compensate the bias that has been introduced by poor choice of f by optimizing only the value of c in the neural network parameterization. So first we will focus on the ideal case, and I will show you graphs like in the previous section. But before, just a reminder of the method to be sure that it is clear. So the first step was to generate a reference dataset by integration of Lorentz 96 equations that has been parameterized with F0 and C0. The second step is to learn beta from a learning sample in which C has also been sampled. Then with the neural network estimate of beta, noted f hat, will be used to generate time series by integration of the first equation, x point hat equals the dynamics plus f0 plus the neural network parameterization. On this orbit, we compute the value of metric m, which depend on c, and we minimize the m to find the optimal value of c, which will be noted c star. So just like in the previous case, I have represented here in this graph the value of metric m as a function of the free parameter, which is c here. And each one of the red dots correspond to an orbit on which the value of the metric was computed, and these orbits are generated using the Lorentz 96 equations. The minimum of metric m is at c equals 10. This is it's quite flat, but c0 equals 10 is the value of the parameter that has been used to generate the reference data set. So it's something coherent that we can find here. If we do the same thing by on orbits that has been generated by integration of the Lorentz 96 equation, where the coupling term has been replaced by the neural network, we find that the optimal value of C star is 9.92. So once again, we are very close to the reference value, and we can say that we have recovered the reference value during the optimization process. Now we can focus on the second and last example, which is the imperfect model calibration. And the major change compared to the previous example is that we use f equals fb, with fb not necessarily equals f0 in this case. However, in the reference dataset, the reference dataset is the same as before, so f equals f0. So this will result in the introduction of some bias in long-term statistics, and we will try to compensate the bias that has been introduced by optimizing the value of c. So the starting points are the reference dataset and f hat that we have obtained in the previous case. We then generate time series by integration of the first equation, x dot point equals the dynamics plus fb, the biased value of the forcing term, plus the neural network parameterization. On compute then the metric, which will implicitly depend on f, and which will be a function of C. And then we minimize the value of the metric MF to find the optimal value of C, which will be noted C star, and which will depend on parameter F. So the baseline to evaluate the correction of the calibration can be a neural network parameterization that it is not possible to calibrate, and to replicate this situation, we use the neural network parameterization that we have obtained previously, which depend on C, but we fix the value of C to C0, which is a first best estimate without using optimization, because this is the value that has been fixed to generate the reference dataset. And so here in black, I have represented the logarithm of metric M as a function of F. So here we no longer see the optimization curve that I have shown you before. Here we can see the influence of or the bias that has been introduced by the choice of F. The dashed blue, line the dashed vertical line that you see corresponds to F equals 10, which is the value of 0, and each dot corresponds to the mean value of orbits that has been generated to compute the value of metric M, and I have also represented 95% confidence intervals in shadings. So when F equals F0 equals 10, we can see that this function reaches a minimum, but when the bias on F increases, we can see that the logarithm of F, so the value of M, the error also increases. So this is the case when there was no optimization on C. But there is a second case that we can study where we allow the calibration of C. So for each value of F, we determine the optimal value of C. Then we generate an ensemble of 25 orbits to compute the value of metric M, and we represent and the result is represented by the blue curve. And as you can see, if we use the optimal value of C instead of the standard value C0, the error remains quite low, and it compares to the lowest value of error in the previous case, which was reached at F equals 10. So we can say that we have succeeded in compensating the bias that has been introduced by poor choice of F by optimizing the value of C only. So this is the end of the presentation. The conclusions are that so first, it is possible to obtain a neural network-based parameterization that can be calibrated online also by adding some influent or sensitive parameters theta among the input variables of the neural network, in addition to the state variable x. The value of this additional parameter or parameters can be tuned to ensure low long-term biases or in the resulting model. And this method has been illustrated using the Lorentz 53 and the Lorentz 96 model. The first example, as well as the first example for Lorentz 96, has focused on the recovery of the reference value regarding a reference dataset, and we succeeded to do so in both examples. And more importantly, we have also succeeded to reduce the value of metric M or the errors when one of the model parameters that cannot be tuned carried biases in the Lorentz 96 case study, and this was achieved by optimizing only one variable in the neural network-based parameterization. The next step will be to implement this method in a climate model for a more realistic case study. Thank you for your attention, and I will be very happy to answer your question if you have some.
Thank you. Maybe I'll start with a question. Have you started trying to implement this in a climate model, or like what do you think are maybe some of the challenges that you might run into with that?
Well, we haven't tried yet, but we have an idea of what parameterization we can target with this kind of method, and of the parameters theta that we can include into the learning sample. I think that we will use this method on the deep convection scheme of hyperschema. And for deep convections, the sensitive or influence variables, theta, are quite easy to determine. This will be something like the detrainment rate or other parameters that have an influence on triggering, like the thickness of the cloud that you need to consider that is a deep convection. But the main difficulty will be to generate the learning sample because you need to make several simulations in order to sample the values of these parameters as well. But I think that it will be feasible.
Hi, nice talk. How many samples do you need? You probably mentioned this, but I might have missed it.
Oh, well, no, I think I haven't, but I'm sure that. So we have in practice for the learning or for the optimization?
For the learning.
Oh, for the learning. Not that much. Well, we have actually we have generated short time series, so the sample was quite big, but we have used 100 different values of beta or C parameters, and the time series were like I think it was like 50 time steps times 100 values of the parameter of interest. So yes, the learning sample is a bit larger than in the standard case, but since we are using time series, that remains manageable.
And would you expect that to change if you have multiple parameters that you're trying to estimate?
Well, we have tried, but in fact, Lorentz 96 and 63 were quite challenging because there is a lot of correlation between the standard deviation and mean values. So this has limited the number of parameters that we can optimize. In practice, it is possible to optimize up to 2 parameters because we have 2 equations in Lorentz 63, and we have succeeded in tuning 2 parameters using our methods. But we cannot tune more than 2. There are 3 parameters, but yes, we have tried and that works.
Thanks.
Maybe one other question, like, does the like the neural network they're using here is fairly simple. Like, do the parameters make a lot of difference, or is that something that you've looked at much?
Well, the learning task is very simple. So I've not mentioned it, but the neural networks were 3 layers deep with 256 in one case and something similar in the other case. And this was sufficient to get a good result. So we didn't try to make something deeper or more complex.
Okay, thank you.
But I think that it wouldn't be sufficient in a more realistic case with real climate models. Maybe because these are more complex functions.
I had a question. I don't know. Can you hear me?
Yeah, I can hear you.
I was just wondering, do you need to have the same parameters in what your kind of training data set or that you're using to generate the training data set and your kind of bigger model with kind of resolved dynamics for this method to work?
Can you repeat?
Yeah, I guess does the model that you're using to kind of train your neural net, the thetas that you want to use in your kind of your subgrid parameterizations, do those need to be shared?
Well, I still don't understand. I'm sorry. I have very poor connection here.
Yeah. Maybe I could type. I don't know.
If you can type it, please. Sorry. Thank you very much. To have the same parameters we want to tune. Yes, yes, we need the same parameter. That we need the parameter that we want to tune in the online model inside the parameterization. In the case of learning from a high resolution model, the subgrid scale processes, we don't have any parameters like here in these examples when we have equations to generate the learning sample, but we can identify some parameters that can be computed. But this needs to be done prior to generating the learning sample.
Okay, so you would have to have like a translation step between like a high resolution model.
Yeah, exactly.
Cool, thanks.
Thank you.